Hello and welcome to the video presentation of the work done by Xavier Matabosc and me, Mireia Tarradellas, for the second assignment of the course Application of MATLAB Octave to Thermal Engineering Problems. In this project, our objective was to measure the discharge rate of a lithium-ion polymer battery at temperatures around -20 Celsius degrees. We will mainly focus on its voltage and on the temperature rise of the battery during discharge.
Another objective was to use some of the concepts learned during the course to better understand them and consolidate their application. In this case, we will focus on interaction between MATLAB and Arduino, binary communications using serial port, and graphic representation of the obtained data.
In order to do that, a MATLAB program that interacts with an Arduino board has been designed. Further on, we will explain in depth the codes of the design programs and the obtained results during the experiments done with the battery.
The MATLAB code manages the communications with the Arduino board through the serial port and stores and represents the evolution of the different measured parameters of the LiPo battery. The code sends orders to the Arduino in a binary communication and tells it what to do. After Arduino has received the order and performed an action driven by its own code that we will explain further on, the Arduino sends information back to MATLAB again through the serial port in a binary communication. The reason we're using this type of interface instead of a more simple one such as Arduino I/O package is that we wanted to create an interface for a high rate of sampling. Although that the development of the interface is more complex, using binary communication, a more powerful tool is obtained, optimizing the Arduino serial port bandwidth. So let's get into the code. The project has mainly two sketches. The MA communication, which is a function that sends commands to the Arduino and receives answers, and the main A2, which drives the program ordering each of the communications with the Arduino and storing and representing the obtained data in order to follow the experiment. There's also a third sketch called postproc, which reads the output data and represents it in graph for better understanding. This code won't be explained in this video because it was not the main objective of the project and it can be easily understood. For any questions about this script, don't hesitate to ask us. So let's explain the main A2 script. First of all, a new file is open in write mode and the port is initialized with all the information where the communication with the Arduino board will take place. All this data is saved in a single structure S, so that it is easier to use in the future. After that, some graphic configurations are set, in this case to represent the temperatures received from the Arduino. How this graphic representation works. A 500 length vector is set, so we only see the last 500 values received from the Arduino, and we don't have to deal with all the data received, so we will only see the most recent values. After that, the axes are set. We're expecting temperatures between -20 degrees and 40 degrees, just in case the battery starts heating. After that, we're going to use an actually 3-axis graph in order to represent the temperature using different colors. Higher temperatures will be represented by red and lower temperatures will be represented by blue, so that it is easier to understand. In this case, the color will be proportional to the height, which is represented by XY, and the height will be actually proportional to the temperature. So we will obtain a color graph with higher temperatures in red and low temperatures in blue, as I said before. And here are the commands to represent and print the graph. Here are the same commands, the same configurations for temperature to representation, and after that the iterations start. On each iteration, at the beginning, MA communications, which we will explain it before, we will explain it after, is called with a single input parameter with all the data from the serial, as I said before here. Then this function returns three different parameters: voltage, temperature 1, which refers to the temperature of the battery, temperature 2, which refers to the temperature of the environment. After those values and some other data to take control of the data received from the Arduino, all those values are printed in the file we opened at the beginning. And after, the temperatures 1 and 2 are plotted, and also is plotted the voltage, in this case in a more simple graph. And that's what MainA2 mainly does. Now let's explain what MA Communications MATLAB to Arduino communication does. This function has a single input parameter S, which has all the information of the port where the communication with the Arduino is taking place. It also has three output parameters, which are the voltage of the battery, temperature 1, which will be the temperature of the battery, and temperature 2, which refers to the temperature of the environment. The first communication is to get the voltage. First of all, we define the command we want to send. In this case, will be a command 1. And why a command 1? 1 will be the command we use to refer to voltage inside the Arduino sketch. Mireia will explain how it works later, but to get a first approximation, when the Arduino receives a 1, what it will do is compute the voltage and send it back. No arguments are needed here, so we set all arguments to 0, and we use send bin C and C to send the bit, in this case that bit, to Arduino. This function, send bin, was given by Manuel Soria in order to establish the binary communication with the Arduino. After the Arduino receives that command, it computes the voltage and it sends back a number through the serial port, which is received by this function. Again, a function given by Manuel Soria, the teacher of the subject, to establish this binary communication with the Arduino. Then this value is converted to double and converted to voltage using that function. It needs to be remembered that this value it comes from a current divisor, and as we will see in the Arduino code, it is computed differently, not only just from the input pin from the Arduino. Then after that, this value is checked, and in case it's not logical, an error message appears. To compute the temperature, to communicate with the Arduino to compute the temperature, the procedure is similar, only a few things change. In this case, the command is not a 1, it is a 0, and after the Arduino receives that 0, not just one value will be sent, but two values, the one corresponding to the first thermistor read and the one corresponding to the second thermistor read. Now, those reads from the thermisors need to be transformed to temperature values. In order to do that, those different parameters are defined. The different resistance, the internal resistance of the NTC of the thermistors at the reference temperature, in this case 298.15 Kelvin. Then the temperature of reference is also defined, and the reference parameter of the thermistor is also defined. Those values, T1 and T2, the reads of the thermisors, are converted again to double, and the temperature values of the battery, in case of temperature 1, and the environment are computed using those functions, which are characteristic functions of the thermistor. Then two checks are made on those values computed of the temperature, and just in case they're non-logical, an error message also appears. And that's what MATLAB to Arduino communication does. Having explained the MATLAB code, let's now talk about the Arduino code and the used hardware. The following circuit was implemented with the two thermistors, an error LED that will blink in case of an error is detected, a thermostat, the voltage divider, and a load to discharge the battery. Now, Mireia will explain the code implemented for the Arduino.
To study how the supply system behaves during discharge in different thermal conditions, a series of Arduino sketches and MATLAB scripts were developed to obtain, save, and represent graphically the evolution of the different measured parameters. In particular, the measured parameters were the voltage provided by the battery and the temperature in 2 points, which are the temperature of the surface of the battery and the room temperature. Only one Arduino sketch was implemented on Arduino. This sketch obtains the required data from the circuit at which the Arduino is connected. First of all, the variables and pins that Arduino will use are declared. Then the loop is executed, and at each iteration, the loop will receive from MATLAB the code of the command that Arduino must execute. According to this code, Arduino will access the corresponding case in switch algorithm. The coding of the command is obtained in binary format by calling the function sgetbin. Sgetbin is a function of the interface sketch binary transfer developed by Professor Manel Soria. Mode 0 is the temperature measuring mode. When it is executed, Arduino obtains from analogic pins 5 and 6 10 values of temperature, then it calculates their average value and sends it to MATLAB by using the function send1bin. What send1bin does is send the value to MATLAB in binary format through the serial port of Arduino. This process is first done for the battery temperature sensor and then for the room temperature thermistor. In both cases, the values of temperature are obtained by calling the function getTemp, which has for argument the number of the pin corresponding to the thermistor of interest. GetTemp returns an integer between 0 and 1024, from which the temperature will be obtained later on in MATLAB. Mode 1 is the voltage measuring mode. If it is executed, it obtains 10 values of voltage with the function getV. The average value of a dose is calculated and then sent to MATLAB. Again, the same value will be an integer between 0 and 1024, which is proportional to the voltage provided by the battery. The switch considers a default case as well, which would be executed if a non-contemplated command was sent due to an internal error in MATLAB, or if measured voltage or temperature was out of the expected range. In this case, Arduino would forever blink an error LED in digital pin 13.
All the connections were made and the battery with the corresponding sensors together with the Arduino were placed in a box as shown in the picture. The battery was discharged 2 different times, one at an ambient temperature of around 23 degrees Celsius and another time inside the fridge where the temperature was around minus 20 degrees Celsius. From the computer, and thanks to the serial communication established through MATLAB and Arduino, we were able to monitor what was going on with the battery inside the freezer and at an ambient temperature. After a certain amount of time, 500 samples have been taken and the graph starts updating and moving to show the last taken samples. Experiments have been manually stopped after the battery reached voltages under 3 volts to prevent the LiPo from being damaged because of a too deep discharge. More details of the obtained data can be found on the report of the experiment. Here are some of the obtained graphs after being processed by PostProx Sketch. Thanks for attending to our presentation, and we hope you have enjoyed it.